I'm Zack. I've done a lot of things in my career. I've worked on cancer research. I've done things for education, improving accessibility for kids with disadvantages. More recently done machine learning at scale with high reliability, and very, very recently, automotive stuff. When you've got software in a car and it might explode. Currently, I work at Oxon Corporation. We have a website. And Oxon is building a platform to help make complex systems safer and more reliable. So that's our deal. I'm going to tell you about empirical verification in Rust. And it's 4:30, so you may be getting a little sleepy. You have to decide, do I actually need to pay a lot of attention right now? Because I don't work on things that might explode. I'm not in aerospace or building biomedical devices. I work more on webby things. But that's not the only dimension that might make you care about verification. Maybe you also care about the social aspect. The thing you are building is going to be used in something that might have an application in a safety critical or high reliability domain, as opposed to just something you're doing for yourself. Or you care about verification because you don't like looking back over your shoulder and wondering if the thing you built a month ago is still broken, or was ever broken, or is about to break on you when you build the next thing on top of it. A different way of thinking about it is that when you are a person and you want to build a thing, take some effort to design it and write the code, and then check to make certain it does the thing you're going to do, you want it to do. If that's irreducible, if you can use more advanced techniques to more efficiently verify your code, then that's less effort for you to spend in making the thing you want to build. Alternately, if you have more efficient or more advanced techniques for verification, you could use the same amount of effort to build a shinier and better thing. So here we are again, empirical verification. That's, trying things out and seeing if they work, but with data. For the sake of this discussion, I want to caveat and say, there's an awful lot of other forms of verification, and they're all very important, and they deserve their own talks, and we don't have time for them. We do a lot of these at my company, because it's important too. But for now, we're just going to focus on the part where you actually execute code. Now, if you actually need to execute code, there's a bunch of ways to do it, and I'm going to tell you about some of them. The first one you should do, if you have some code and you want to see if it works, does what you need, you should probably make an example. Build a tiny binary that just exercises your code, and you see if it does what you want. Cargo has a built-in facility for this, such that if you just toss a file, hi mom, into a particular spot in your project, you run cargo run example, it'll tell you which examples you have, and you fill out hi mom, and it runs it. And you can verify with your eyeballs that some aspect of the program does what you want. Now, the next thing you might do is say, well, that was cool, I put my eyeballs on something, but I'd like to automate it a little bit more than that. I'd like to actually have some automated verification. The way that you would jump to solving this idiomatically in Rust is to use the built-in test framework. For those of you who are new to Rust, this means that when you have an annotation on a function, a little test attribute, at some point or another when you run cargo test, there'll be a sufficient analysis of your binary to pull out the functions that are annotated as such and execute them. If they panic and there's a failure, you know about it. Cargo test, it's very easy, you should use it. When you start building these different scenarios, they end up having some repeated components. You have some code under test up at the top. You set up a scenario. Let's new up that food, and let's bump it a little bit. Let's mutate the state. And then finally, we're going to assert something about it. We're saying, we understand what should be happening here. Let's just check. And you tell me if it failed. In addition to doing this for tiny little pieces of your code, just a single function or a single structure, you can do this scenario-based testing for much larger pieces of code, perhaps whole CLI applications. Here we have an example stolen from the wild for the WASM bindgen CLI, where you can use, with the help of some handy test libraries, just execute your whole dang CLI and assert that the output matches what you expect. if you're in the webier side of things, there's just about every Rust web framework out there has some sort of testing facilities for setting up just a single route test, or setting up a mock route or something like that, or actually firing up the web server and then targeting it directly. In any case, the point is that this pattern of think about what's going to happen, specifically give it a particular input, and then assert on the output is scenario-based testing. And it's pretty good. We've gotten a lot of use out of it in the world of software programming. And there have been a lot of libraries built in Rust to make this convenient. You can write your tests in a different form of layout that's more like another language. You can add mocking to make it so that the complexity is bounded for the various portions that you're assembling into your scenario. If you care about asserting that a behavior is of a certain pattern, there are libraries to help you do this in a way that's comfortable and fitting for both the domain objects you're inspecting and the way you want to think about it. Finally, more recently, there's been some libraries to facilitate capturing the OK cases that you want to insert against that scenario capture, snapshot testing. It seems like I'm going really fast and I'm a little out of breath. It's because, while this stuff is great, and please go back and look at the video and go find the ones that appeal to you, there's better things to come, because there's a but coming. Scenario testing is great, but at some point or another, your ability to enumerate over and understand all the reasonable scenarios you need to build for the code under test gets tougher and tougher and tougher. Wait, how am I going to test this one? Is even was easy, but now I have to think about cosines. What am I going to do there? Wait, this one's got a kind of complex output space. Do I need to separate those out? What if the input space has got a lot of data in it, and I'm not even certain the size of it, and there's question marks and there's branching structure that's not obvious? At some point or another, the human becomes the limitation in deciding the reasonable set of inputs you want to put into your system. Even for something as simple as this, a simple summer. Adding two things together. Like, I've tried out some cases. I want to assert the behavior that, when you add two things together and they're unsigned, the result is larger than either, or greater than or equal to either. I think I've been enough, don't I? Nope, I definitely don't. But I don't want to have to think about it, so why not just have the computer do the thinking for me? Let's try out all of the possible inputs. Exhaustive testing. Let's make a for loop. Let's walk through every single one of those U16 instances for both of the sides and assert the result. Definitely going to feel very confident that this code is correct. This is the sort of thing you would only do if the code was foundational or high criticality and of small enough input size that it actually makes some sense. By the way, you should be happy you did this because there's an error in this code under test and panics because there's a saturating out there, and those test cases that you made, you thought up in your head earlier, you might not have remembered to think of something pretty close to U16 max. But, like I said, the applicability of exhaustive testing is rather limited. It only works when the input space is rather small, and the things under test are rather deterministic. The ones at the top there, feasible. With enough multi-threading or computational budget to throw at it, you can solve exhaustively programs that you care about pretty completely. Anything down at the bottom, kind of tough. The strings, those are more or less unbounded. 4 U32s, that's going to cost you. Getting that into the every commit-based testing lifecycle is going to be painful or impossible. So what do you do when you can't ask everybody in the nation what their favorite flavor of ice cream is? You sample it. You do a representative random sample of the possible code paths of execution by selecting just a limited set of inputs from the massive space of possible inputs. This is also called generative testing, or a particular instance well known as fuzz testing. Fuzz testing is available in Rust. It's great. It's really powerful. We get to use industrial-grade fuzzers in Rust with not a whole lot of effort whatsoever. The pattern looks roughly like this. The window dressing changes a little bit between the available fuzzers, but they all look more or less like this. This is testing the base 64 crate. This is pulled from the wild. It follows the pattern of you have a macro or some other input method that is handing you a byte, a pile of bytes, here a slice of bytes. And then you're setting up a test scenario here, encoding and decoding some data, and asserting what you want over it. And the fuzzer is responsible for just giving you as much data as you can possibly have, and eventually discovering when you found something that fails. Great for parsers, great for penetration testing, when you've got anything that deals with random sets of bytes. You can get higher level structure, but you kind of have to do it yourself. Now, the way that this is integrated in Rust is often through, I recommend looking at the Cargo Fuzz project. If you look at the layout here of what you have to do to get that thing I just showed you to run, is put in a specific directory and call the cargo function. That sounds really similar to making an example file. In fact, the level of difficulty is pretty similar to just making an example. It's really, you suddenly get a much higher degree of coverage of your code input space. Now, it's not just that you're generating random bytes. These fuzzers often have a additional feature that goes above and beyond. Beyond just feeding data to your test case that tests your code under test, fuzzers often use instrumentation of the code under test to gather data about when you execute the code, if given branches of your code are being executed, and using that, guiding the set of bytes that are passed into the test case. This feedback loop can be used to more efficiently explore the input space, and therefore get a greater chance that you're going to cover the branches of interest in your code more completely. So this is a feature of fuzzing that puts it above and beyond running RAND in a loop and just generating it that way. So coverage-guided instrumentation here. There's a number of fuzzers for Rust. I haven't tried out Angora, but the others are all solid, and you can pick them to your choice of interface. But what if you don't want to deal with just a pile of bytes? I want to work with my domain object of interest, of foo in this case. If I'm working with most of the fuzzers nowadays, I have to interpret them manually from this giant pile of bytes. And that gets rather tedious. If you've got the ability to wait for the fuzzer to figure out that you can deserialize or serialize, maybe you can go directly into objects that way, but it's not always easy when you're down in the depths. Wouldn't it be great if you could just directly jump to having a randomly generated instance of the thing you cared about and validate against that? Well, we're coming up on property-based testing, which is a notion which combines the sample search space that we saw in fuzz testing and adds a notion of structured input. You care about how you got to the scenario inputs, and those scenario inputs are more closely aligned with what your code is actually dealing with. It also has a cool thing called shrinking, which I'll get to. Property-based testing is pretty great. It's like the unit testing that you saw earlier, but with a much greater proclivity to guide you in the direction of thinking about your domain objects and their relationship to their actual behavior in a way that you can't, in a way that allows you to explore all possible scenarios because you can't explore all possible scenarios. What I'm saying there is because you don't know exactly which input is going to come in, you are forced to consider more general properties of the system. Now, doing this in Rust has a learning curve. There's some libraries to do that you can use. You can use quick check, you can use prop test. I'm going to use prop test here for the examples. Here we have, within our prop test macro, a test function that looks rather similar to what we saw earlier, except for that there's some special details in the parameters of the function. We're saying here, please generate for me a count, randomly selected from the range of 0 to 30, and a message that is a string generated that conforms to this regular expression. And from that, I'm going to build up my object and assert it instead. It's pretty awesome. If I want to check that I can successfully parse a particular pattern of string, I can make anything I want. Similarly, if I wanted to more tightly control the set of values that I'm inputting, I can adjust those ranges or say, just give me any old U64. Now, when I start moving away from the core primitives that are provided by these testing libraries, I might want to start building up layers of domain objects that are constructed for the purposes of more tailored scenarios. So I can make a function that makes arbitrary foods according to a given specification and use them in successively more complex layers for the properties that I want to analyze. Now, I'm not going to go into too much detail, but when you start being able to make complex objects in chains like this, you get the ability to build really dynamic scenarios. Scenarios that don't just do one input in, one input out. It becomes rather easy to make complex chains that, for lack of a better word, are a little bit more customized. Now, I'm going to talk about shrinking just very briefly. Shrinking is an analysis tool that property-based testers have where they analyze the methods that they used for creating your inputs and attempt to produce a minimal reproducing test input. So this is an example stolen from the workshop yesterday where I was building tests for an inline application. And it turns out that it had a problem with handling white space. And the property-based tester initially tossed in this big old random string and was able to automatically reduce it down to a simple fact that any old space will cause it to fail as opposed to this larger pile of characters at the top. Not something that most fuzzers do nowadays. You would probably get just that top thing as a failure reproduction for most of the other fuzzers. So that's kind of the main gift of property-based testing above fuzzers is closer alignment with your code domain. There's something missing there. Fuzzing does have instrumented feedback. You've got coverage guidance for your inputs. Wouldn't it be great if you also put them together? People are starting to think this direction. You can do this with prop tests with the pass-through mechanism. You can do this with quick check if you've seen a recent post and read it on that topic. There's also the new fuzz check library and framework, which is attempting to do structured fuzzed input, specifically for Rust. I haven't had time to experiment with that enough to evaluate its efficacy, but good things are happening in this domain. I've got a more complete analysis of all these different techniques in the context of dimensions of applicability and usability here, but I think we're out of time, so just catch me afterwards for that. Before we close up though, you have to ask, I've put some effort into making these tests, and I think they're okay, but are they actually good tests? How do you know when to stop? The answer people usually give you is, well, when you get to 100% code coverage, okay? That does mean that you've executed a lot of code. It does not mean that it's good tests. One of the analogies I use to explain this to junior engineers is code coverage is like that square there, and your code is the circle. You can use code coverage to discover if your square is not overlapping with your circle at all. You're not actually executing any part of your code. And you can determine if it's approximately the right size. You're executing more or less all of the code paths. Executing all the code paths is definitely not the same thing as exploring the possible input space of your program, let alone the entire internal space of the program. This is where we come to the notion of mutation testing. A well-established pattern that's not exactly common in Rust yet. The mutagen framework is under development and may be available, but let me try to give you an intuitive sense of what this concept is. Have you ever written something in Rust? You wrote some code, and you wrote a test for it, and you ran the test, and it succeeded the first time. And you're like, I can't believe this. I must have messed up the test. The test must be way too easy. And you go back, and you break your code to see if the test fails. Mutation testing automates that process. What it does is, you write your test suite, and you leave the test suite alone, and it automatically, through manipulation of your code, goes and messes things up. It adjusts your constants. It changes pluses to minuses. It generally mucks with things. And if your tests say, hey, you just subtracted instead of adding, but I'm okay with that, then your tests are no good. Similarly, you can use mutation testing as not only a way of guiding your completeness of your coverage of all the erroneous situations, but also a guide of how tightly your tests are conforming to the space of your code. If you have way more tests than necessary, your mutation testing will take a long time, and you may be able to complete some of your actual test units. All right. This has been empirical verification of Rust. There's more things to come. Thanks for your time.